Hi everyone. Today we have Alexandra from Google DeepMind, and she will present their work on like autonomous agents in the era of foundational models. So before we start the talk, just some rules. Like if you have any clarification questions during the talk, you can ask them. Just raise your hand, and I'll wait for me. I'll give you the mic. And for people online, just type your question in the chat, and whenever the time is right, I'll relay it. And at the end also we have like 15-20 minutes like for a dedicated slot for questions. So yeah, that's basically it, and I'll just hand over the mic to Alexander.
Do I need to use a mic?
No, I think
Yeah, okay. All right, awesome. Well, thank you for having me, and thanks everybody for coming on your day off. that goes up above and beyond expectations. It's really a pleasure to be here. Feel free to interrupt me, ask questions. We can go as fast as slow as it's needed. So I want to talk to you about autonomous agents for all or real world, and what I mean by that. This would be any system that does something useful for somebody. And this can be autonomous car or a robot or non-embodied agent or so on. And they have tremendous opportunity to help millions and billions of people. For example, 15% of world population or 1 billion people have some sort of disability. So the potential is huge to make really positive impact there. But these systems really to kind of get them where they ought to be have certain common set of challenges. They all need to perform well. They need to be realistically generalizing across the tasks and so on. And it needs to be cost effective to train them. They need to be tractable, right? And historically, before the foundation models and so on, you can kind of think of these as a cost generalization quality triangle. We've been tackling the edges of the triangle and so on. Last several years, foundation models came to the scene, and we're starting to see kind of more tackling this inner side of the triangle, really large models and so on. So today, what I want to talk to you first about specialist agents is kind of more of the older work, and I'm going to focus mostly on the robot navigation there, maybe some web navigation, to kind of give just a sight how we were solving these things. Then I talk about the generalist agents from the perspective of the data, especially using expert data to kind of cheaper forms of the data. And then at the end, we'll talk about current foundation model self-improving agents and where basically what LLMs are bringing to the agent in RL community that we kind of struggled before. So just to set up the scene, this is real-world robot navigation. This is the same task. The robot needs to go to the sink in the environment, and as we repeat that task, environment changes. Now, the path is blocked, right? It needs to go around and figure out what to do. This is reinforcement learning policy running on the robot, zero-shot transfer from simulation to a transfer. Robot does not have a map. The only thing it has a LiDAR observations. There's a custodian coming. We did not script this. He needs to avoid it. So it's a LiDAR observations, and the actions are linear and angular velocity to it. And basically the goal is in polar coordinates getting to the sink. Now people move, there is interaction there. It's actually, and now it goes around. So this is the real world challenge.
Yeah. Is the simulator of the same room, or do you train like various rooms?
Couple of slides. So more broadly, in robotics, robot sensors, dynamics, it's kind of physical bodies, right, and so on. And even onboard compute determine how they can move, what their abilities are. The aerial robot will go from A to B flying over. The quadruped will go down the stairs. Wheeled robot might need to take an elevator, but they can still potentially go from A to B. Or in some cases might not if they can't fit under places and so on. So they come in all shape of sizes, and we need to kind of figure out the methods that can trade all these type of different shapes and robots to get from A to B. So what's with the classical approach? The classical approach has observations, then we have perception and SLAM, and they have motion planning and control. And this is all good and fine because we have separation of concerns, and we have the modularity, and life is good until you start to put it on a system. And then what it happens is that we have human in the loop integration, because the motion planning did not know about the shortcomings of the controls, and the motion planning did not know about the perception shortcomings or the abilities of what is seen in the dynamics. And it's very complicated and it's time consuming. And basically every time we put in a new system, it's a new problem. So just kind of for inspiration, how humans learn. And this is not kind of to go in that direction, but it's kind of good to look at. First, basically our body is evolved to fit our environment in the range of tasks that we're going to do. And general evolution does that, but there are other ways to do it. Then we interact with the environment to learn the skills. And here is my daughter interacting with the environment and learning about obstacle avoidance. And then once we have skills, we learn these predictive models. We call them intuition. We say, hey, I have intuition that this works. The reality is intuition is your prior experience baked into prediction, right? Can I fit under this? Can I go through something? I don't need to hit the wall to know that it's going to hurt. It's my prior experience. So we learn these predictive models. So can we bake that into the prior? So what's kind of broken with this pipeline? It's open loop. So first off, biological systems operate with the same information. So if we kind of have the pieces, let's add observations to each piece. And then let's close the loop from the feedback loop from what happens in reality when you run this to the back to kind of have these predictive models that can say, hey, this is feasible, this is not feasible, and so on. So let's talk about the control piece. This is the robot video that you asked. And the idea here is, okay, I just want to go to a goal. So my observation is a reinforcement learning problem. Observations are these noisy LiDAR observations. We just kind of feed last three. White means big distance, black means short distance around me. This is 270 degrees around me. Feed prior three and the goal. Actions are speed, basically linear and angular velocity of the speed. Environment is basically this top-down map of the office with no obstacles. And that's it. That's the environment. It's not the same one. What's the goal? Our objective is that the goal is reached. That's a sparse reward. And we're going to do exploration. That's not going to get us anywhere. However, we do have a good intuition what that reward might depend on, how far I'm from the goal, how far I'm away from the nearest obstacles, right, and so on. There are features that we know. But the question is, how do we combine these features into the dense reward? And then there's also a question, this was way back when, what neural network architecture to choose and how many layers, right, and so on. These are hyperparameters of the system. And it's very time consuming to train them and so on. So we opted to learn them. We're using evolutionary methods to do that. Basically, we spin off a bunch of mutated rewards with the different features. We evaluate with respect to the goal reached. This is our true objective. And then we evaluate how it goes and select the next version. Basically, we're fitting here reward to the learning algorithm. And there is kind of follow-up work that kind of shows that actually different learning algorithms, depending which RL algorithm you use in different parameterizations of the reward work. And then the second loop, then we select the policy and the reward weights. The next round then fits the neural network to the reward that we learned. And kind of do the whole thing, select the policy. So what we have at the end, basically this is the environments that we're training. They're all office type of things, or actually maps of several offices. And the idea is to kind of transfer to the unknown. We train this in simulation, but we add a whole bunch of noise to the sensors, actuators, and kinematic model. And then we randomize initial and goal conditions, so let it kind of go around. The objectives and the learning method is the same, and it's basically off-the-shelf RL. And this does actually zero-shot transfer to different office environments, to dynamic obstacles to an extent, the different robots, and we apply them to all these other modalities of the robots. One thing that's really interesting here is that it was able, this was one of the first policies that could do point-to-point navigation for robots with the kinodynamic constraints. It's a two-point boundary system, and generally controllers for these systems did not exist. This provides approximate solution. So you can kind of go nearby and reach a goal or not. So let's kind of take a step a little back. So what is the reality of kind of evaluating and building these agents? We have basically human that does RL, and then we train, and then we evaluate in the real environment, and then we loop back the performance. And there are all these kind of hyperparameters along the way, right, that we need to do. So basically, human is doing sequential decision making, right? Well, we know how to solve sequential decision making. So we can automate this and put a RL agent or any kind of learning agent in the loop and formulate this as a two-level optimization problem, where in the first loop we're optimizing hyperparameters, in the second loop we're learning, and then we go back and forth. And it's the kind of whole automated RL field that kind of went from there. All right, so that was point to point. Now we have good policies. They were not cheap to develop. Running all these kind of trainings, we've done this 2018. It was about a week of training on 100 GPUs. Not cheap, but you have them and you can use them. So now the question is how we can best reuse them. So we want to go back into the planning one step above. The planning should basically propose the new goals. If you have a higher level goal, what are your intermediate goals? And we're assuming that we have this control policy, whether this is RL or it can be any other control policy for that matter, but we're going to assume that it's not perfect. But the insight here is that by having it roll out, we can observe how well it performs, and we can bake that into the planning. So one of the kind of first ideas here was the PRM-RL. PRMs are probabilistic roadmaps in sampling motion planning. Basically, you take, you're assuming that you have the classic sampling-based planning, you're just assuming linear controls are going along the line, and that's always feasible. We're assuming one of our control policies, that's obstacle avoidance, able, and so on. And then you take the map of the environment and you sample it randomly, and then you try to build a graph by connecting adjacent nodes. And you connect the adjacent nodes. In classic is if there is a straight line between the two. What we're proposing here, hey, let's use our controller, roll it out n times, and then if it's sufficiently above the threshold, it means that these two are likely connectable, so let's connect them. And that way we kind of have these probabilistic roadmaps that are custom field tailored to the robot and the abilities of that control policy. The problem is, again, this kind of doing all these rollouts is still expensive. For some of these maps, it takes 100,000 edge connection attempts, which then means rolling out all these policies. But it closes the sim to real gap pretty well. And there is actually example here in the building that it's not connecting the two. And like, okay, we're not clear why. There is a pillar here and the control policy was pretty noisy. So we basically figure out that it was not safe that robot was not safe to go through that. So then from there, can we then speed up, instead of kind of doing this manual and expensive roll-up, can we do these learn predictive models of given what I'm seeing now, what my observations are now, what the future is going to look in time delta t. And there's a whole line of work for helping the one-time exploration, roadmap planning, multi-agent approach where they're basically learning how other agents are going to behave, and then we can kind of co-plan if I observe you, and visual navigation and so on. So I'll go through reachability and this visual navigation sub-goal. Yeah.
So correct me if I'm wrong. So for every office that you want to train, you need to have a map and the simulator to train that, and then deploy the agent in office.
For short-term trajectories, so A to B, you do a zero shot. You don't need a map. So if I'm going to go to the door or so on, it does not need a map, does not need anything, right? If you're going to do longer-term planning, and maybe the insight here is let's go downstairs and outside. For that, I kind of need to know a bit of the environment, right? And need to know where to go. So some insights here is that actually there is a structure in the environment. So if I need to go upstairs, outside, or to the next conference room, and so on, my probably first waypoint ought to be the door. Because I don't care where I'm going. If I'm going anywhere outside, my goal is not here, it needs to go to a door, and I fit to the door. I'm not going to go through the window, right, because I'm not a flying robot, right? But that's a local information that I can observe right now with the sensors, right? And doors and this type of thing, this is actually the critical states, is a critical state that kind of puts you in a position where you can explore more. So yes, when you're doing the longer planning, you need to have a map that then you search through the space. We build a roadmap. Yeah, that's a one-time setup. If you want kind of deploy it to a new environment, you can take the roadmap. And actually roadmaps that we're using here are literally the screenshots out of the map that we were having in the buildings. These are familiar, right?
So once in the classroom, people don't really have to.
Also, you mentioned about next future state prediction, like in delta t time. So is it more like successor feature predictions, or is it more like next token predictions in large language models?
I didn't hear the first part.
So you said like in this part, you would want to predict where the robot is going to be in delta t time steps. So is it more like successor features? Like what's the right way of to think about these predictions?
Think of it more as a learning heuristics at this point. This is older work, so it was all done, I don't know, 2019, 18, that time frame. So the idea was that, okay, one thing that, well, we can go through reachability. Basically classic motion planning relied on lots of heuristics that people had built to do. So that might be a swept volume. The idea is like, okay, I'm going to calculate this very expensive swept volume for the motion. And if I minimize that volume, that means that it's likely that motion is safe because I'm just kind of taking less space. So it's like that I'm going to hit something. Collision detection is done with very expensive computational geometry methods. We're kind of doing all this kind of voxel calculations and so on. But if you think of it, if I know generally and I have good sense of my body and the space around me, I know that I can't go through this. I don't need at every step to calculate, right? It's all prior experience. So these kind of go in based on these heuristics that people have been using in motion planning and say, hey, we can learn this one, we can learn this one, we can learn that one. So it's not successor features, it's basically more practical.
So it's more like general value functions in some sense, like different cumulants.
Yes, I would very much like to see something like this kind of transfer to DRL and so on, which is partially what I'm talking about this now.
Thank you.
Reachability. The idea here is that we want to have the robots with kinodynamic constraints that are not easy to navigate, to be able to get from A to B. And one way to go about this is now called RRTs, or rapidly growing trees, that you basically sample. You have a point where you're right now. You start sampling from there, and then you keep kind of sampling, and you bias your sampling towards a goal if you need to and then you hope you reach the goal or you don't reach the goal. And very time expensive and so on. So the observation is here that, okay, if I sample here, if I have n samples at my disposal, can I learn how likely it is for me, or how long it's going to take me to reach that sub-goal based on my observation? So think of a car, right? And if you want to move the car forward, this is maybe, it's going to take you 1 second. If you have moving that car and there is a wall in front of you, and you need to park your car behind that wall, you kind of look at it and says, yeah, I can do this, but it's going to take longer, right? So the idea is, can we learn that predictor that associates your visual input, what you see, and where the goal is as an input, and then learn how long it's going to take you. And the way we do that, okay, training environment, pick, and then randomly sample. You observe the sensors and time to reach, the rollouts. You learn that time to reach predictor. And then once you are doing the planning, now with that predictor, you can eliminate points that are going above the threshold, or just kind of pick very small sample of the points that you need. So here is example. On the right is the ground truth. On the left side is the actually learned predictor. Black means it's a short distance or short time to reach, and then white means it's close to impossible for that particular controller. And when we put that to grow the trees, we see that we're getting basically we're getting the shorter paths and faster planning, especially kind of on the shorter distances, which is expected. And you can the blue one is the classic RRT, how much the tree grows, and green one is with this kind of guided predictor, because you can eliminate a whole bunch of things before we start. And you can see down kind of the tree growing until it reaches the goal for the exploration. I'm betting this can be used for value-based stuff, but go ahead.
Did you also use generalize in training the network, or you want all of the data just feature?
So the network that we're learning here is the predictor. This is a simple neural net. We assuming that we have the control, which in this case was RL policy, but it can be any controller for that matter. And we're just kind of rolling it out, get the data set in supervised learning. It's as simple as that. Okay, so that's that. And it saves a lot of time in planning, especially for these hard to plan models. Second question is here about the visual navigation and navigation around humans. All the work that I talked before was using LiDAR, which kind of just give you the safety distance. Basically, can you pass or can you not pass, but it's missing completely on any semantic information and so on. So if we're going to do obstacle avoidance around the humans, we have a problem. We can train in simulation, which then sim to real gap visual policies is hard, to put it mildly. We can train it in reality, which then poses two questions: safety and sufficient diversity of humans. I bet you find enough volunteers for that job. So training in real is not an option, doing a sim. So how do we construct sim that can do visual navigation sim that can go basically, that can zero shot transfer? So the insight here is actually combine two data sets. that we know transfer. One is the surreal data set of humans that we then place in this Stanford large-scale 3D indoor data set, which we know transfers. And then we augment humans on the scene that we can change features about them. We can change their gender, we can change their color, we can change their facial features, body shape, and motion. Now we can simulate, right? Now we can do fun things. So the question here is, in this case, we're assuming classic controller. And again, in the privileged environment, we go in the simulator, sample a whole bunch of initial and conditions. We whole bunch of diversifying data set. Select the goals, use the MPC to solve the problem, and then basically measure the cost of every solution. Now that we have basically your sensors, what you see, and the cost of, and the waypoint that's being proposed, and the cost of that waypoint, we train, again, a predictor model that then in a planning phase, we say, okay, here are my possible goals that I can do. Here is the one that's the lowest cost, or the end of the lowest cost. Go in and select then and go from there. So what are some insights here? One thing that's interesting is, so red is dynamic human, blue is the static human. So we're not, the static human is the policy that's trained without dynamic humans on the scene. In a case where person is moving this way, the static policy is going in front. The one that's trained on behind is going behind. Oops. And basically what we're saying is, I think it's actually associating the leg positions with the direction of the movement. So, and then in this case, kind of goes behind. We also see that baseline cuts off human, and this does not happen in the reality. And this is a zero-shot transfer, and also the camera has different field of view. I think we trained in simulation 65, and this is 50 or 47. But it avoids it. Reaches the goal. This is the baseline. Not doing that. We can go to next one. All right. I'm going to switch a bit to the web agents.
Have you tried generalizing the robots? Like instead of one robot. So what if I use the policy of that robot and then deploy a different robot?
We use them for differential drive robots. You had a fetch robot there that had an arm, which we're not using arm for the navigation. And then there was the basically fetch base that did not have the body. It was the lighter and so on, faster, and that was. Generally did not go in that direction, because if you look at the robot, its body, it's the permanent thing, right? Environments and the task that a robot should do over life cycle of the robot will change. Its shape and kind of robot body will not. So it made sense to kind of invest more into making a good policy that fits that particular robot than to kind of do a generalization. But I want the recipe to be applicable to different robots, right?
About the last part, I think I missed something. You train on a surreal data set, which is essentially rendered and then human motion, enabled that natural dynamic.
It's a superimposed on the surreal.
I think someone yeah. So at the test time, you just take that policy, train that surreal, and you how like because are there like encoders in between? Is something
So,
like
so the observations are visual observations, and apparently sufficiently good enough. The office data set, they've done prior work that kind of shows that you can do zero shot sim to real transfer. It was not sure for the surreal, but humans were kind of sufficiently good. And I mean that was one of the challenges. Like, can we do this for the visual navigation tasks?
incorporate some kind of like shading, because like natural lighting.
Yeah. So it'd be interesting to kind of go and see further the robustness of that solution. But that was a challenge, like want to do additional training. All right. Sure. Yes.
What makes it so in the first part you had
Uh-huh.
the controller doesn't know how to take out the old.
So the reason we could get away with the static obstacles is because we're doing decision making at 10 hertz, right? And there is last three observations, so kind of gives you a little bit of that history of the motion and balancing out the noise. But then every 10 times a second, it's a new world, right? So I don't care that the obstacle moved, I need to kind of replan or decide, yeah. All right, web agents. I'm gonna kind of shift gears now. If we're gonna, navigation was point to point. Now, if you want to do different tasks and do this compositional task generalization, how do we go about that? Generally, the idea here for the web navigation, we're focusing on the form filling. So if you want to do the form filling test, actually similar to robotics, it's a manipulation. You need to enter several fields. You need to hit the search. New room opens up. You need to do some manipulation, right, and so on. They're repeatable elements, just like in physical robot, in physical environments. We have doors. That would be your search button, right, that opens up the new room, and so on. And the drop downs and repeat and whatnot. At the time when we're starting doing this, the existing models were only doing imitation learning with millions of interactions, even for these simple things. So one question here is, if we're going to tackle generalization, what kind of generalization can we expect from the system, right? If I train a robot, to speak naively, to do robot navigation tasks, can I expect it to generalize to manipulation? And I say no. But why is that? Right. So we put here formalism for the compositional task in the web navigation space through the Petri nets. Petri nets are basically graph representation of the tasks. And the idea here is that you have these primitives. This would be your drop-down box, your first name, your last name, and so on. And in order to basically proceed from these form-filling tasks, you have some of these kind of elements that they all need to sync at the gate one, and then you have some others, right, and so on. So there is a shape, there is a grammar that we can describe these Petri nets. And then it turns out that there is one-to-one basically going from Petri nets to POM MDP definition, which then basically becomes that our generalization question is find a single policy that maximizes the expected return over this family of POM MDPs that are induced with the family of the Petri nets. So if I'm given n these primitive actions, here we're doing 45 primitive actions, and I have grammar that describes the Petri nets and all the POM MDPs that ends up, that's basically the space that we can expand on. And then we created basically an open source GMiniWeb benchmark that can do this. And then the training was a curriculum. And basically there are two two nets. One is the designer LSTM that basically proposes and creates the new environment, rolls it out. And its aim is to do just the right challenge. Then given that environment, we train population of these web agents, and it returns the regret, basically the spread between the best performing and the worst performing, and the best agent's performance to the LSTM as a training feedback. And basically the loss for the designer network is that it wants to, if the challenge is too high, it needs to kind of reduce the number of elements that it's being given. And then if the best agent is performing well, it wants to diversify onto more applications. So it's kind of this min-max situation going on. And then we're evaluating this on out-of-distribution tasks. And what we see is basically that as we go, environments become more complex. The blue line is here, our method, and then the other two is paired and the manual curriculum. We also see that they do generalize to the unseen environments. Oh yeah, this is, yeah. The environments become more complex as we're progressing with the training, and the distribution of the primitives over the training of the designer net shifts more towards elements that actually you need to perform the task. Because the designer has no idea that you need to have submit button, that you need to have OK button to complete the task. So it learns that along the way, and it's like, okay, now environments that I'm designing here. Interesting tidbit here is that these environments that it generalizes don't need to be realistic. It can have 3 first names. It needs to be similar to the robot navigation. Basically, the environments that we're training is a superset over the real environments. All right, so this was kind of went way too long, but what are some takeaways? Add noise to the simulation to characterize the sim to real gap, automate the learning whenever you can, look for the local substructures when you can, close the loop, assume imperfect data, and look for curriculum. All right. Then came the generalist agents and the transformers in this 2021-2022 period. Whole bunch of work that happened in that space, decision transformers and so on. So how do we kind of bring our single robot, little short couple of neural nets layers into this space? So one of the first, and I'm going to go basically going from imitation to most expensive to train in terms of the expert knowledge to the least. So one of the first models that came was the scene transformer in this space. It was a BERT architecture that proposed a joint prediction of all agents on the scene, including the self-driving vehicle and everything that's on the roadmap. And then it predicts the next step, and you can mask it. You can mask the goal to predict what the goal is going to be. You can mask other agents' goal, so you can kind of predict where this car is going to go, and so on. It was kind of one of the first models that set the stage for that. On the web agent space, the things that we trained, now that I just spoke about the designer and so on, was using very simple HTML. It was very clean, small synthetic forms and so on. The question is, how do we process the full unprocessed HTML? No simplifications, right, and so on. The LLMs that were out at the time did not have any HTML in the training data set. So we proposed 3 basically canonical tasks for the HTML, which is semantic classification, understanding what this field is. Is this a first name? Is it a last name? Is it ship date or arrive date or whatever that might be? What is the description? One thing that's hard in the HTML, it is a tree that's kind of flattened, right? So if I want to know what is the label for this field, it's an email, that label might be somewhere else in the document, and the email address field can be, I don't know, your emergency contact. I just checked in for the flight, the emergency contact, or maybe my emails. The description matters there. And then what would be your navigation action, what you can do to the task. So the insight here is that we found that there is a common crawl data set, which is a snapshot of internet. And people write enough comments. And there was enough comments in that code that can say, hey, this is the first name and this is the first name. These two go together and so on. So we extracted data set, which was a small data set, 200K demos, fine-tuned one of the pre-trained LLMs, and we got on these tasks better performance with basically 200 times less data than the prior model. So it's like, foundation models actually have something can help us. And it's also kind of a variety of these tasks that were not trained before. And again, pre-trained model did not see HTML ever before at the time. All right, but how we go beyond imitation, because this was a clever way to get expert demonstration. Multi-game decision transformers came at that scene at the time. Basically, multi-game decision transformer rolls out the trajectory. It also does the predictive, but it has the reward in there. So it's using the mix of the expert level data. So you need expert, you have some novice, and so on. It still requires some expert data. And then you can query it. Interestingly, you can query it to play at the novice level. If you specify reward low, you can specify it to run as the expert level if you specify the high reward, and so on. But what you cannot do, well, it can play 40 games and you can also fine tune to the next one. But what you cannot do with it is you can have it performing better than the best data that it was trained on. So how can we break that? I think some of us talked about this yesterday. In, again, autonomous driving and any safety critical information, we have lots of boring data when it gets to safety critical scenarios. And back to that robot visual navigation around humans, we can't safely collect data around in the safety critical scenarios. So our data, we can have lots of data, but that data is not evenly distributed, and we have giant holes of missing data where we need it most. So the idea is, how can we combine the data that we have with something like reinforcement learning that can then basically keep the data in distribution when we're near the imitation data that we have, and then fall back on the reinforcement learning when we start going out to distribution. So doing this helps improve the safety and reliability in the driving policies, especially when it gets to the more critical scenarios. So the lower is better here. More to the left are the most difficult scenarios. So the behavioral cloning was having close to 6% failure rate. The behavioral cloning soft actor critic cut that down to about 2.5%. And we can kind of see some of the scenarios that successfully won. What was the secret sauce here? The transformer observation encoder and training on difficult examples from the prior work. And then the loss was really what you would expect, the combination of the RL loss and the imitation learning. The reward was basically don't collide, so safe and stay on the road, follow the goal. And then we also experimented with making a progress, which did not make much difference. What's interesting, though, is that it retained the human-like behavior. So here, these two are talking about the acceleration, so how fast you kind of slam the gas or the brake pedal. The blue ones are demonstrations, so human driving. These are trained human drivers. Orange is here RL, which kind of see RL either goes or it doesn't go. It's all in or it's not, and you don't want to drive in it. The The behavioral cloning soft actor clinic has basically the same similar pattern with a little bit kind of here on the wings, but you know what? It kind of solves these critical scenarios, so that's okay. The same thing with tire angles, how much it steers. The classic RL basically just uniformly steers and it does not do anything. Where the behavioral soft actor clinic is actually more aligned with a human distribution. All right, so that was all kind of good and fine, but we still, yeah.
So do you, because we have introduced Avid in the pipeline now, you observe that to get like better scores on the various tasks that you showed, these agents also require more samples because they are essentially learning from trial and error on top of some information.
Yeah, yeah. But we're using, okay, so in order to do this, we build a Waymax, which is distributed very high. I think that does the simulations at 100 hertz. The very distributed, high efficient simulation. It's open source, so you can use it if you want.
So the increase in score is the cost of more samples and then more.
Yeah.
There's always that trade.
Another question regarding like adding RL to behavior cloning. I wonder if the behavior cloning kind of caps the performance of the model and prevents it from going beyond human performance.
Well, but in these cases, when you get to the safety critical scenarios, it outperformed. Now, there is no data there, right? We don't have the data of human performance in these safety critical scenarios, and you can get it. So I don't know. Right? I mean, to be fair. Yes. All right. Okay, so as we kind of went through this, and large language models came to scene, and there was all this supervised learning happening and so on, RL still had a problem. RL would not kind of scale up to the large capacity models. And one of the reasons that RL and Rishabh here came in, that basically supervised training benefits from regularization when there is a large capacity model. In sequential decision-making problems, when your observations, subsequent observations are very similar, we see a collapse of the subsequent features. So, solution very simple, add a regularizer. It's as simple as that. And that kind of enables RL to start working at the large capacity models. It still did not work for transformers, work with the ResNets and so on. And the question was why. So the second insight here is that supervised learning uses categorical cross entropy as a loss, whereas we're using regression. And surprisingly enough, when you switch the regression for the categorical loss, now you suddenly start having really good performance with the large transformer models. And we're kind of seeing across the tasks on the chess, on the Wordle, on robot manipulation, and so on. And also we're kind of seeing again that we're adding more data, we can fine tune to the new methods. So finally, RL is kind of getting there. All right, so what is some basically meta-analysis here is that for the generalist agents, model size matters, which kind of now it's not in, we sort of know that by now, and then we can fine tune for any new application that you want, add some data and you can fine tune it and so on. That's good. The second one's interesting is that data matters. And data matters in two ways. One, how it's really distributed in the kind of space of fold coverage that you need. And you can safely remove redundant data as long as you're not sacrificing diversity. This was from insight from the RT1 paper. The other one is curriculum matters. And if you think of curriculum is sampling data out of the same distribution in different order, right? So how the order of the data that we present to the agent makes huge difference. And I'd love to kind of see more work, kind of theoretical work of where, how, what the data is, and so on. So in kind of this section, basically some takeaways is that realistically, we need to be practical and mix expert data with synthetic data and basically RL collected data and so on. The data distribution matters, and we know now that for the large capacity RL, we need both regularization and cross-entropy loss. All right. Now, LLMs are here. So what's the big deal? One thing that kind of we've been struggling, so I'm going to go over several things that they actually enable. In kind of classic robotics and agents and so on, our task specification was really suboptimal, to put it mildly. Reward is not the way to specify a task. We've been doing reward shaping, we've been doing points, and so on, not very natural. What I really like is you can say, hey, robot, pace forward fast, and then it goes. Or say, how about we go backwards, right, slowly, and then it starts going back. Eventually it will. That's much more natural way to interact. And LLMs actually start enabling this. So in this case, the interface is the foot pattern. So you're having a 0, 1 when the foot is down on the robot, and that's 1, and 0 is the foot is up. And we can kind of define different gaits. And then for training, this is busy, so just kind of listen to me. Basically, we're training classic controller that takes in a contact pattern for a very simple bound, trot, and pace. And then this comes to the controller. RL part is whether it kind of executes that, robot falls down, and so on. And then if that works, that's our controller. The second part then is we add the LLM on top of that, which is only prompted. And it's prompted your dog, foot contact pattern expert. Here are some gaits, and kind of gives you an example. It's a few shot, and then you put these two together. And LLM does not know anything to do about the controller. Controller does not know anything about the LLM. But here we go, LLM produces zeros and ones, that controller happily takes it. What's surprising is, okay, go slowly, go fast, right, so on. It's I can do things like this. Back off, don't hit that squirrel. That's the top right. Active, the ground is very hot. That's your bottom right. Actives, you have a limping rear leg. Or, good news, we're going to a picnic, and he keeps leaping up and down. That's surprising. That's never seen there. And this is the generalization that I guess LLMs picked up out of the various YouTube videos of the dogs running and so on. And it's able to generalize and create the foot patterns that never saw before. So.
Have you tried asking it to swim?
Yes, and it just sits there. Yeah. Well, I don't know if it was swimming, but it was like, okay, can we do jump over the ball, right, or things like that it was out of the distribution. Yeah. But it was, okay, how much we can push this? Did not quite expect that. But this opens up really use of the system to many people that are not experts to be able to interact. I mean, we're seeing that today, right? So natural interactions is really key. Second piece is that all these systems have very different observations and actions, And this is kind of to your question, like separate policies for different robots, right, and whatnot. So we're kind of custom designing, okay, this is a real robot, we have these actions, if it's autonomous car or the web agents are kind of having these own specific actions and so on. And that's suboptimal. It's actually preventing this cross-domain generalization. And I'm going to kind of use an example here. The insight here is that LLMs write code, and code is pretty universal interface. So now we want basically web agent that takes basically unprocessed HTML. This is from CNN. It's 7 megabytes long observation. That's what unprocessed HTML looks like. The M1, basically you put a natural language instruction. I'd like to check parking lots along the way from Stanford University to the painted ladies with the best option map at the website. And then you give it a starting website, and it goes in. Okay, this is here example of searching 2-bedroom, 2-bathroom in San Diego. Goes in, selects pieces, and so on. In the process, basically every step along the way creates the code that's being executed in the loop. And basically with about 200 self-collected demonstrations, we have basically per domain generalization. So how it works, for the web agents, we have starting URL and starting instruction. We're using actually the foundation model with the HTML that I talked before that takes these two and outputs. It's using the local global connection because we found that basically you need attention on both sides since it's a flattened tree. The end has basically outputs the snippet of the HTML that's relevant and a small planning instruction. You can think of it as really perception and planning in the same swoop. And then out of box LLM takes these two and produces the code that then is being executed, and we start with the next observation in the loop. That's the pipeline. Once we can have a pipeline and you give it a task to train it, you can give it a reg expression with, okay, if I'm looking for the apartments, here are a number of queries, search X number of bedrooms, and basically give about 20 variations of the queries that then it can substitute. And then it does autonomously tries to collect the data. And if it fails, that's a failure, so that's not a good instruction. Basically fine-tunes itself on these self-exploration. So what we're learning here is that this modular approach with a specialist language model does work. And you kind of need the modular approach for this. That we're seeing the broad generalization. And on the real website, we're getting 65 to 80% success rate. This is a research paper. There's a big safety concerns here. And yeah, because we don't want agents to be running code willy-nilly. Yeah, it was a moment on the whiteboard like, yeah, we should not be doing this. This is not going consumer facing, but we can do this. So LLMs bring us universal actions and planning. It is here. Okay, third thing, they talk. And one thing that's been basically difficult is modeling both environments and the social interactions. And LLMs can talk, and they can actually impersonate people. The question kind of poses here, do they have human consistent personality types? So we work with the psychometricians, and we want to evaluate whether, according to the big 5 personality traits, are they consistent, and can we use the instruments that are being used on humans to evaluate personality traits in the LLMs. So there are some examples prompts, and we're going to basically establish the construct validity, which is very kind of rigorous process in psychometric to make sure that we're measuring the latent variables, in this case, personality traits. Turns out, yes, they do, especially the larger models they have more human personalities. We'll come to that. And they need to be instruction fine-tuned. These are these examples here on Palms we've done since on Llama, ChatGPT, Mistral models, and so on, and the results are consistent. So one thing, why human consistent? Turns out that when it gets to the personality traits, there are some correlations in behaviors between different personality traits. So example, extroversion, there is in humans, and this is humans here, there is 58 positive correlation with a positive effect, and there is 0.2 negative correlation with negative effect. When we put this on the LLMs, they have stronger correlations. So what does that mean? How do you interpret this data? It is more human? We beat the humans. They're basically more exaggerated. They're more biased towards whatever they need to do, right? So there it is. So then the question is, okay, can we modulate that? Can we shape and control the personalities? And we came up with over 100 different adjectives that then you can basically control. I want extremely, very, or a bit, and so on. And turns out when you kind of add these to the prompt, it does actually control personalities in a way that you would expect them. And then the question is, okay, that's nice, but does it hold down for the downstream tasks? And yes, it does. The red line is here human prediction, and blue one is LLMs. Again, they're outperforming humans in being more human. But they basically, you can recognize what the methods can recognize what the personality type is based on the text. So what does that look like? So high agreeableness. You can say, I want to be just like my mother because she's the most moral person I know. I love my mother. The lowest agreeableness, I have to clean. I'm very bad about keeping the house clean. Extroversion. Wow, my buddies are here. It's been a long time. I forgot how much fun we used to have together. And then the lowest extroversion goes, watching reruns of my favorite TV shows. Just give me. So it's interesting to kind of see that now we have they can impersonate, and we can kind of control that impersonation, which kind of lends itself to potentially kind of building synthetic personas. Or you have a question, or
No.
Okay, or you're just kind of mildly uncomfortable. Okay. Yes. So the other piece, and I'll give credit to Vio here, these are new synthetic videos. How much work we've done doing the thermodynamics and kind of fluid dynamics simulations and so on. Here is pouring maple syrup and coffee down, or the lights and so on. This is pretty incredible. Where that kind of leaves us is that now we have an option to do synthetic worlds. Natural interactions, lots of tasks, planning and action, synthetic worlds. Okay, great. But they also have interesting prompting properties. They can learn. They can learn from themselves. So in context learning, great. We know few-shot learning and so on. That's all good and fine. You add more examples, they're going to learn better. Again, back to the question, you need expert. Well, it turns out you don't. If you have unsupervised in-context learning or reinforced in-context learning, which basically model proposes the label, and basically that's kind of rewarded with the ground truth as yay or nay, turns out that actually performs better in some cases. So than in context learning with ground truth. So this kind of light green is the ground truth runs, and then dark green and blue are unsupervised and reinforced RL. And in many cases actually does better. All right, so they can kind of teach themselves things. Second thing, and this is going to be at TyClear next week presented, they can self-correct. In math, if you have a problem like this and say, hey, there might be an error in the solution above because the lack of understanding of the question, please correct the error if any and rewrite the solution, if any. And then kind of goes on and rewrites and fixes the problem. It does not come natural. There are two things that are kind of happening without help. Is that one, there is a distribution shift with the offline self-correction. And two, as kind of SFT and STAR methods, which are kind of basically baselines in the self-improvement or self-supervision, they kind of start biasing towards not changing the answer between the two terms. So what we do is basically you introduce the loss that works in two stages. In stage one, you actually, so we basically have first answer and the second answer. So on the first round of training, we say, hey, do worse on the first turn, so you do better on the second turn. Basically, we're creating a gap in the answers. And then on the second set of training, this is the RL loop, right? We're basically rewarding for both, but there is a little bit of the reward shaping. Now we can say, okay, you can do answer either one of them, fine, we're good to go. And that actually, this is the main insight, that we explicitly need to encourage training to get this gap in the behaviors. One kind of the lessons learned here is, again, Goldilocks principle with the data, that if it's too similar, it's not going to learn anything from the corrections. And then if it's too kind of different, so this kind of just gives it just enough difference between the two terms. So the results on math and human eval, the accuracy, so this is the score, this is the proposed method, outperforms the SFT, STAR, and kind of other methods. Even kind of on the first turn for math, on the second turn for sure for humans as well. So where we're going with this? The natural interactions open a whole bunch of tasks. Universal actions and planning allows us now to apply that to the wider crowds of the systems. And synthetic worlds and basically the synthetic environments allow us to do all this in simulation much faster than we've done before. And we have self-improvement methods, right, that they can basically start creating this self-learning loop. So where does that take us? The autonomous driving had this concept of the levels of the automation. It basically says level 0, there is no automation. Level 5 is full automation, and then in between is like drive assist systems, right, and so on, or this works in certain environments, highways or residential streets, right, and so on. And the reason they developed this is because we can then reason about the evaluation and safety of the systems. So level 5 can be deployed anywhere, level 4 not so much, right, and so on. So we try to do something similar, and this is not by any means a definite way, but is a way to start a conversation to talk about what would be the levels of AGI. And kind of look at the axis, on the y-axis from the narrow to the general AI. So narrow is basically very specific use case, and then general is anything and anything possible that humans can do. And then level 0 is no AI, and then level 5 is superhuman AI, and we're basically looking at the levels based on average human performance. So no AI, narrow calculator, right? does one task, does that task well. General no AI, this would be your mechanical Turk. Does any task a human can do, there's no AI. It's all human labor, right? And then kind of going into the emerging AGI that, okay, it's performing as an unskilled human and so on in broad levels of the tasks and so on. So kind of thinking we're kind of in this state now, not quite at the competent AGI. Competent AGI would be performing better than average human across the board. All right, so what are then the implications? On kind of different axes, we can look at if there is no AI, humans doing everything. In level 1, AI is a tool. Basically, human is in control, and basically just AI automates simple tasks. Then becomes consultant, it's invoked by human, and so on. 3, now we're collaborators, we're equal. 4, AI takes the charge, right? And human is kind of in the backseat, and then 5 is fully autonomous. You can also look at the risk as a society based on each level. The level 1 can bring de-skilling and disruption of the established industries. The consultant, we can have over-trust and kind of over-reliance of the AI that might not be too good. We can have targeted manipulation, and so on. And then we can also look based on kind of the capabilities of the AI for each of these levels, what levels we need to kind of achieve in the performance of the system to enable them. It's a conversation starter, whether that's a way to look at it or not, but I think we ought to be looking at. So where does that leave us? It's been incredible progress in the AI. I think things are accelerating and now keep accelerating. There is no doubt that we're building really powerful technology. The one that can really transform all of our lives if we use it for good, for education, for sciences, right, and so on. But then at the same time, there is the dark side of that coin that in wrong hands and not used and regulated well, it can go wrong very quickly, right? So I think all of us working in this space should really have this on top of the mind. But I don't want to leave you on the grim note, so here, let's enjoy the dog going on a picnic. Thank you.
Yeah, thank you for the amazing talk. And now just raise your hand and I'll come to you. Give you the mic.
This is also kind of in the conversation starter type, but I think maybe another axis or way of looking at this is like, how are we applying the technology? Because like I feel like once it gets to a point, like I don't know enough about this to really say, but for example, I'm curious if we can extract something about biology from AlphaFold. Like, is there something we can learn about what it understands about folding of proteins?
Yeah.
And like, so can we learn from these things to become more expert ourselves?
That's an interesting question. I was wondering about that because as we're kind of looking at here, de-skilling, right, and so on, at the end of the day, we're interactive system. And again, not my expertise, so I don't know, but I was wondering, 100 years ago, 200 of pre-industrial age, what were our cognitive abilities, right? Pre-calculus, right, and so on. So we evolved and we changed as well. I don't know. I think we kind of as a field need to open up and to more adjacent fields and bring expertise where we don't have it.
Hi, thank you for a great talk. I have a question about the quadruped experiments. So I think some of the gate that doesn't look like any kind of animal gates. Do you have any rationale where they're coming from?
It doesn't have what?
Doesn't look like any kind of animal gates. For example, the one with the 2 front legs hopping and the back leg jogging.
I have no idea where. Yeah, for which one particular? That's a good, because I'm not a locomotion. We'll get there. Okay, which one?
For example, the upper left one,
Okay, the picnic one.
the picnic one.
It does not jump like that. I'm asking.
Maybe.
Yeah.
And I think like this kind of decoding the footstep planning,
Yeah.
it's very, very specific to robot locomotion community. Do you think a large language model have that kind of knowledge?
So
For me, it's not a very kind of general knowledge.
So apparently it did, and at least in this case, we need to use GPT-4, GPT-3, Gemini did not work. At the time, at least GPT-4 had enough knowledge. So I don't know what was in their pre-training data set, right, that was able to extract that.
Right. And another question I have is some of your work is about self-improving. Do you see any chance in my self-corrupting what you have learned before? Does the opposite direction?
So if the prior works with kind of this encouragement of doing the spread between the turns did kind of lead to the collapses. Mind you, this is all done on math and coding where we have the ground truth. The big question here is, can we combine also learning the reward, in which case if you start learning the reward, you can go very easily out of distribution and then things can go south very, like in the wrong direction. But as long as you kind of have the grounding in the reward, should be fine.
Okay, thank you.
I have a follow-up question regarding I think one of the slides you showed that without enforcing the structure, the model seems to collapse, like the mode collapse where it fails to fix its previous error. We've seen like I read a similar paper saying how like Llama isn't able to learn how to reason and self-correct, while Quen was able to do that. Kind of curious to hear your thoughts, whether the structure that we're building into the RL pipeline is something necessary or just a temporary fix.
That's a good question. I do think this is actually a temporary fix. One thing that I was curious about this paper in particular is this a two-turn thing? So is this more of this expectation maximization algorithm, or the flavor of the tool level optimization where we first do this and then we do that? Now we're kind of spreading the distribution and then we're training on the distribution. We go back and forth in order to climb up. Or this is more of the annealing thing where we start with big gap here, like think of it exploration rate, right? Or gamma factor that then kind of changes along the way. It's not quite clear, and the fact that you kind of need to encode number of turns in the loss function, it more seems like, okay, yeah, this is a sign that it's working, but it's not undefinite answer.
Thanks.
So we have a question online from Sunny. I'll unmute you. Just 1 second. Or sorry, I mean, you can unmute yourself and go ahead. Yeah.
Sure. Hi, thanks. Alexander, are there some thoughts or research directions on having, say, a team of humans and multiple agents like quadrupeds and, deciding how to achieve a high-level goal? Like who does what part of the goal to achieve a downstream task? Are there thoughts around, going around compositional decision-making across multiple actors? What are your thoughts on that?
So I'd love to see more work in that space. One work that we had a few years back, and I didn't talk here about it, is it was basically two agents that need to rendezvous. So they need to meet in the environment without having the predefined goal. So the idea here was then that if one agent, or it was actually an agent, it was not two agents, basically that each agent observes every other agent's motion and learns this predictive model that based on what they see in the environment, what the environment looks like, where the obstacles are, and where the other agent is, that they see how they move, and after time delta t's, I say, okay, they're there. So I'm going to assume that was their goal, so I can now backtrack back there. So now if I have this model, and learn the self model as well, now if we kind of have this predictive model, we can say, hey, okay, if we want to kind of go all together, let's propose several points, see if these are feasible for the other agents, or kind of what's going to be in the next state, the most optimal position, and then kind of do this basically model-based RL planning with these learned predictors along the way. But kind of going into more of the multi-agents, I think this is going to come.
Sure. Yeah. Thank you. And just a follow-up question: are there new threads that you can suggest on cross-modal reasoning and planning? Like you have to reason and plan from a visual sensor, but then you have to act in a unknown terrain or unknown environment. Are there new directions around this area?
Well, the foundation models have been, there has been lots of going from the same sensors to the new environments is not that new. I think that's standard. Where there has been lots of work kind of going to cross-body. Now back to your question. It's not here. And also looking at combining the data using the videos from YouTubes and so on to augment the expert demonstrations and so on, and then expand into different action spaces. And there's lots of work from Google DeepMind in that space and so on. And there are data sets now.
Sure, thank you.
Oh, well, if nobody else, then I actually have a question. So about the in-context learning part, you mentioned that like they can learn new tasks. How do you quantify whether the task is actually novel? Because it might have happened that during pre-training, it has seen a wide variety of tasks and it essentially covers a lot of things, right? Like from the function space. Maybe it's not a new task.
In which context?
So from the in-context learning slide.
Oh, context learning.
Yeah.
Because we trained a new language that we knew it wasn't in the distribution. So first off, we see that we can do a label reversal. So if we basically you propose it that black is white and white is black, which you did not see in the training and so on. So let's see. The default labels would be your light green, so here on the top. And then the few shot prompting are the flipped labels that are going in the light yellow. So we know that wasn't in the data set, and you can basically undo the bias, the learning bias that it had. And then we used it for, it's not here on the slide, but we use it for new language, low context language that wasn't there.
And just like what's your take on like why in-context learning happens? Like, is it because it has seen to do predictions and for many different tasks, and now just with few samples, it can basically like learn to, infer the weights and apply that function? Is it like a meta optimizer, or what's your take on it?
So this is guessing. The intuition is that with the more context, that there is so many redundancies, right, in the different paths that the data is going through, that when you're providing more context, that it's basically sharpening that path. Where is it going? Or the intuitively, if you're looking at an ultrasound image and you don't know that you're looking at an ultrasound image, it looks to you like clouds, or right, until somebody tells you, oh, this cues you in, right? Oh, this is, and kind of we see all along our reasoning, any cues that we get actually help us with the reasoning. So I think that's really the in-context learning. And few shot examples and so on is really one way of providing more context. But yeah.
Okay, any final questions from the audience? All right, then let's thank the speaker once again and
And thank you for coming on a day off.